Hey, what's up guys? It's Dr. D-Flo, and I usually avoid clickbait titles, but this MDPE10 screw extruder from Massive Dimension is the most expensive 3D printer item I've ever featured on this channel. This behemoth has a volumetric flow rate of over 5 kilograms per hour. Just imagine how long it takes for your desktop 3D printer to go through 5 spools of filament. This extruder chews through that amount in just 1 hour. In today's video, we'll take a close look at the extruder, wire a brand new electrical cabinet to support its power-hungry heaters and motor, and of course, fire it up for a couple of prints. So with that, let's get started.
Dr. D-Flo.
In the comment section of my recent Orange Storm Giga video, many viewers highlighted a significant mismatch in the 30 millimeters cubed per second volumetric output of the filament extruder compared to the printer's massive 800 by 800 by 1000 millimeter build volume. It would take weeks to fully utilize this volume, and the cost of filament for such large prints would be prohibitively expensive. These observations led to suggestions of replacing the filament extruder with a pellet extruder, which can melt large quantities of more affordable plastic pellets. However, fitting a large pellet extruder onto the existing gantry is impractical. Even my smaller MDPH2 extruder is too large. While smaller pellet extruders are available on both commercial and DIY markets, it's crucial to understand that size profoundly affects their efficiency. The length of the screw plays an important role in ensuring uniform melting and mixing of the pellets. Larger pellet extruders also feature wider openings, which facilitate more consistent flow of plastics. Therefore, when discussing plastic extruders, bigger isn't just better, it's exponentially more effective at melting plastics. I'm going to walk through the features of the new MDPE10, which I'll refer to as the 10. And during this tour, I will make comparisons to the smaller 2. I should mention that I have both written and video guides on the basics of screw extruders up on my website and this channel. So definitely check those out if you want to learn more about screw geometries, die lengths, and other specialized extruder topics. Let's start with a basic overview of the 10. This extruder weighs 13.8 kilograms or 30.5 pounds with approximate dimensions of 550 millimeters long by 190 millimeters wide by 280 millimeters deep. It has a stated throughput of 5.8 kilograms or 12.7 pounds per hour of PLA. For those who prefer volumetric flow rate, that is 1280 millimeters cubed per second. This massive extrusion rate is supported by 1000 watts of heating and a 750 watt AC servo motor. The nozzles are shipped with a 1.5 millimeter bore, but can be drilled out for larger extrusion widths. In regard to supplying power to this beast, you can see that we have a yellow and gray cable for connecting power and reading the temperature probes. If you open up this front panel, you have access to the terminal blocks to swap in a longer cable or rewire the extruder as needed, which is a nice touch. The motor and encoder cables are separate, so there are 4 thick cables that need to be managed in addition to the pellet tube. I plan to go with an umbilical style system, but more on this later. Next, let's perform some comparisons between the outgoing 2 and the 10 to justify the lengths I had to go to get the printer ready for this big of an upgrade. The most obvious difference is the longer and more pronounced barrel, which of course houses a longer screw. The effective length of the 10 screw is 390 millimeters or 15.5 inches, which is twice the length of the 2 screw. Doubling the number of screw flights increases the residence time of the material in the barrel, allowing for the pellets to be sufficiently melted before exiting the nozzle. In a way, this is analogous to increasing the hot end length on a filament 3D printer's extruder for more conductive heating to achieve a greater volumetric flow rate. However, a key advantage with a screw extruder is that a longer barrel also promotes more shear heating, where the mechanical motion of the screw is converted into thermal energy. This is a crucial factor for why larger screw extruders are more effective at processing plastics. Interestingly, both the 2 and 10 share the same diameter screw at about 16 millimeters or 5/8 of an inch. Consequently, one rotation of either screw will move a similar volume of material as they share the same flight depth at the entrance for the pellets. So for the 10 to extrude its advertised 5 times higher volumetric output, the screw must spin 5 times faster than the 2 screw. This will be an important consideration for the larger motor, which we'll discuss later. The 10 is compatible with the same screws found in the X6 filament extruder, which I've previously covered and are sold by Massive Dimension's sister company, Filament. This compatibility allows the matching of screw geometry to the material being extruded. For instance, screws without a taper, such as this one, are ideal for thermally sensitive plastics, while tapered or high compression screws are better suited for more robust plastics that require greater force and heat to melt properly. This flexibility allows the tin to maximize the extrusion rate for different plastics without significant degradation. Removing the sheet metal from the barrel reveals another upgrade the tin has. 3 separate insulated sections of the extruder, which correspond to 3 of the 4 heating zones. Unlike typical filament extruders, where the temperature setting is uniform across the entire hot end, the tin offers these 4 differentiated heating zones to initiate the melting of the plastic pellets and to account for the heat generated by the screw's rotation. This control helps prevent overheating, particularly near the exit of the extruder, ensuring the material maintains the right consistency before being deposited on the build plate. The 4th heating zone is hard to see, but it's where the pellets immediately feed into the screw. You can imagine that if this section is too hot, the pellets would stick to each other, preventing the consistent feeding of material. Again, I talk about how important these different heating zones are in my basics of screw extrusion video, but the most important takeaway is that they will afford significantly more control over the extrusion process. To continue talking about the consistent feeding of pellets, the feed throat of the tin is 6 millimeters or 1/4 inch larger in diameter than the 2, a seemingly minor detail that significantly impacts performance. Bridging is a common issue in smaller feed throats where pellets align and jam against each other and the throat walls before reaching the screw. Previously, in this build series, I've demonstrated using a vibrator to dislodge stuck pellets. However, frequent use of the vibrator not only increases energy consumption, but can also affect print quality due to the vibrations. With this larger feed throat, I expect to see a more uniform material deposition as the pellet should flow more consistently into the screw. Now, I'm not going to forego a vibrator, as simply turning it on every now and then can save a print. However, this time I'm not going to devise my own solution. Instead, I'm opting for a Massive Dimensions feedstock agitator. This is similar to the one I previously installed on the 2, but instead of rotating an unbalanced mass, this one moves a slug back and forth with compressed air. This vibrator is installed under the top plate of the extruder. Let's turn our attention to the motor. As established earlier, we need a motor that can turn the screw 5 times faster than that of the MDPH2 to achieve the 5 kilogram output. The 2 used a Technic ClearPath 280 watt DC servo motor with a max reported speed of 840 RPM. This motor drove a 10-to-1 gearbox to get enough torque to propel the molten polymer sludge forward. It's unlikely that the gearbox was driving the screw at 84 RPM due to restrictions on melting. Nevertheless, the tin will need to be equipped with a much faster motor, and it is. The tin's Sure Servo 750 watt AC motor can operate continuously without losing torque up until 3000 RPM. This motor also drives a 10-to-1 gearbox, which allows for a screw speed of up to 300 RPM, even higher if full torque is not needed. Now, before we get to hooking up the motor and the rest of the extruder, I want to briefly talk about costs. Likely the most popular thought will be, I would rather buy a car than this $20,000 extruder. Well, to be blunt, this extruder isn't for you. And frankly, it's not for my DIY printer either. All of Massive Dimensions promotional material show this extruder on an ABB robotic arm that cost $50,000 used without a control cabinet. So yes, this is for industrial applications, most likely for R&D or high value products, but it's very cool that they're letting me play with it. Okay, next let's move on to wiring up this extruder. To support the additional heating zones and to install the larger servo drive that comes with the tin, I'm going to have to add some new components to the electrical cabinet. But as you can see, there's no way anything else is going to fit in here. My wire management is probably what receives the most criticism out of any of my content, and rightfully so. But I have 2 excuses. The first is that I see my projects, especially this printer, as perpetual works in progress. I always think to myself that once I'm finally happy with the configuration of my machine, that I will then tidy up all the wires. Of course, I'm a tinkerer, and that day will never come. And the second excuse is that it's easier to be organized when you have space. So why didn't I just buy a larger electrical cabinet at the start of this project? Because these things are crazy expensive. My current electrical cabinet was almost $500. Talk about a boring thing to buy with my fixed budget. Right now, the electricians and panel builders are probably rolling their eyes because an uneventful day in the wiring trade is a good day. You don't want to see smoke and sparks, and having the space to properly route wires and provide clearance to hot electrical components is critical for a safe and well-functioning machine. I hear ya. So as much as it hurt my wallet, I purchased this $1,100 cabinet and spent another $500 on all the fixings to properly route and terminate the wires. In addition to this video, I also created an article on my website covering my newfound tips, equipment, and supplies, which are not only useful for building large panels, but also wiring smaller CNC machines like desktop 3D printers. Now to talk about the cabinet in more detail, its interior dimensions are 36 inches long, 24 inches wide, and 12 inches deep. This is twice as much space as the outgoing cabinet, but weighs 35 pounds more. At 85 pounds, it's too heavy to hang off the side of the 3D printer. So I constructed this aluminum extrusion stand where the back legs reach up and support the enclosure. I added casters just to make it easier to move around while filming. So what is going inside of this cabinet? Well, in part 2 of this series, I explain the role of all the common electrical components needed to make this printer run safely, such as the fuses, contactors, and solid-state relays, as well as the Duet 3 ecosystem of controller boards. If you haven't already, then check out that video, as I will be focusing on the upgrades needed to support the new extruder, which includes the larger servo drive and relays for controlling the extra heating zones. I also decided to take this opportunity to double the stepper motor's supplied voltage from 24 volts to 48 volts with this new 1000 watt power supply. The rack and pinion stepper motors have to rotate quickly to achieve the desired print speeds, and a higher supply voltage will prevent their torque from dropping off at high RPMs. Another motor that will benefit from higher power is the extruder's 750 watt AC servo. The motor combined with the 4 250 watt barrel heaters means that the extruder will draw 1750 watts. This is too high of an amperage for a standard 110 volt outlet and therefore requires a 220 volt connection. If you remember, I wired the old extruder and actuators to 110 volts so that I could use a small battery backup system to keep the printer moving in the case of a power outage, which was actually quite common during the summer that I first built this printer, but less of an issue now. However, with the 5500 watt bed heater, this printer will need 7250 watts or 33 amps at 220 volts. This doesn't even include the linear actuator motors and auxiliary components such as the solenoid for the pellet conveyance and vibrator. In practice, it is likely that the printer will pull a much lower amperage, especially if I stagger heating up the bed and the extruder, but nonetheless, this still exceeds my only 30 amp 220 volt outlet in my garage. So long story short, I'm going to still wire the stepper motors and supporting equipment to a 110 volt circuit. However, it won't be difficult to switch everything to 220 volt in the future. So coming into the box, we will have 110 volt and 220 volt AC. But once inside, various power supplies and controller boards will convert this power into 5 separate DC voltages, ranging from 48 volts for the motors to 3.3 volts for the signal coming off of the Duet boards. I purchased separate color wires and terminals to differentiate the 7 voltages from each other, which should help avoid the expensive mistake of exposing an electrical component to the wrong voltage. I also got my hands on several different gauges or wire diameters. Larger wires can carry more current before overheating. In the past, I would use the same wire gauge for most electrical connections. Of course, the wire was sized for the highest load that it would carry, but this often led to unnecessarily large wires for low current communication. The reason I did this was cost, as I had to buy quite a few different spools for this upgrade. But hey, we're going for perfection. I do want to point out that I wrapped pairs of wires with these cable sleeves. This is an unnecessary step, but because I built the cabinet twice, once for testing and once for the video, I wanted to keep the wires that started and ended in the same location together. I marked the sleeve wires with my new Brady M210 labeler, which is life-changing when used with the self-laminating wire wrap labels. In the past, I used normal labels, which stuck out as little flags on the wires. This is much cleaner. Continuing with the organization, I will run cable trays all over the back panel, which keeps the wires from bird nesting and covering up the electrical components. Of course, these trays will take up quite a bit of space, which is why I have left them out on past cabinet builds, but they really tidy everything up. To separate the AC power from the low voltage DC signal, the AC will be run on the left of the panel and the DC on the right. The last thing I want to point out before we get to the wiring montage are these Wago DIN mounts, which allow you to attach everyone's favorite toolless splicing connectors right into a DIN rail. I'm sure my schematic might be missing a connection or two, but these low-profile mounts and connectors make it easy to adapt on the fly. You can find more handy tools like this in my article on my website. And with that, let's get to the wiring. If you're starting to type in the comments about how I bought too small of a cabinet again, go ahead and hold that backspace button down because I don't want to hear it. I'm convinced that no matter how big I go, it will always be too small. But because everything is a little bit cramped, especially near the solid state relays as well as the servo drive, passive cooling is not going to be sufficient. So I'm going to install a fan on the top of the enclosure just to make sure we get enough cooling in this area. I also drilled a cutout in the front panel for the disconnect switch. Admittedly, I'm worried about the length of the servo drive cables, the encoder, as well as the one supplying power to the motor. So I've decided to drill holes in the top of the enclosure, which will be the easiest and quickest access to the servo drive. With the back plate installed, I can now fit all the panel mount connectors to the pass-through plate that sits on the bottom of the enclosure. I'll catch back up with you when that's complete. So I take back all my complaining about the cost involved with properly wiring and organizing the electrical cabinet. I'm pumped with how clean it turned out. Okay, so a little bit of an abrupt transition, but while wiring up the extruder to the electrical cabinet, I discovered a familiar problem. The tin comes with these 4 PID controllers to report and control the temperature of each zone of the extruder. But wiring the heaters and thermocouples to these controllers would require manually setting each zone's temperature before pressing print. I would rather let my printer's Duet 3D boards regulate the heating zones, which can then be set in the Slicer software and can pause the print if there's a heating fault. However, the problem is that the stock temperature probes are not electrically isolated from their sheathing, which introduces electrical noise. You can tell because there is continuity between their leads and housing. Unlike the PID controllers, my Duet mainboards are very sensitive to interference and are not able to read these thermocouples without throwing an error. I encountered the same problem in part 1 of this build with the MDPH2. So I need to replace all 4 of these quarter 20 threaded thermocouples, but the only commercial replacement that I could find were these $300 RTD 1000s from McMaster-Carr. But as mentioned earlier, I try to avoid buying both expensive and boring items, so I made my own by drilling a hole in a quarter 20 bolt and then stuck a Slice Engineering PT1000 down the bore with some thermal adhesive on the backside to keep it from falling out. That was the easy part. The hard part is why I'm sitting next to a disassembled extruder. The 2 thermocouples closest to where the pellets feed in, around here, were difficult to access. I had to unplug everything to remove this back panel to reach thermocouple number 3. For number 4, I had to drop the motor in the back. These are the 3 distinct heating zones, which each have 2 ceramic heater cartridges that run their length. The 4th zone is less of a heating zone and more of a cooling one, as you can see this aluminum block with fins machined in it trapped between 2 push and pull fans. Again, if the pellets melt too soon, they will block the feed tube. However, there is still a heating element in this section, as some high melting plastics can benefit from softening earlier in the extrusion process. With the new temperature probes installed, I'm going to get the extruder buttoned back up and finish wiring all the other components to the cabinet. Next, let's take a look at the web interface for this printer to see how it handles this multi-heating zone extruder. Here you can see that we have 1 tool and 4 separate heaters. You won't be able to achieve room temperature in one zone and 200°C in the neighboring zone, but enough of a temperature gradient is possible to optimize the melting of the plastic. Check out the extrusion of the tin's first pellets. Before we start the first print, I want to run through some smaller upgrades that I haven't touched on yet. The first is the floating head assembly, which I first put together in part 6, but have since added a switch at the top of the travel. If the extruder is pushed too far up, which may occur when a print lifts off the bed, then it will trigger the switch, pausing the print. Several viewers commented that I can use the same mechanism to touch off the build surface as a probing mechanism, and why yes? Yes, I can. I must admit, that is a little unnerving to watch, especially with how expensive the glass build plate is. So for bed mesh leveling, I will use a magnetic probe, which attaches to this lattice barrel sleeve. I designed this sleeve to not only serve as an attachment point for the probe, but to also hold 3 blower fans. Together, these fans will pump out 56 CFM of cooling, with these shrouds pointing the airflow right at the nozzle. Printing overhangs or small features will benefit from the immediate cooling afforded by these fans. If you are curious how I designed this sleeve, I started with a solid body in Fusion 360 and then applied the volumetric lattice structure tool. In this menu, we can select different lattice shapes such as gyroid, cross, X-cell, or even a custom geometry. Next, the size of each repeating unit can be changed. One tab over, we can select the density of the lattice. A lower solidity will decrease the wall thickness of the lattice, resulting in a lighter but also weaker part. The fans and shrouds are mounted through heat set inserts, so to make sure there is material around the holes for the inserts to grab onto, a solid offset can be applied to any selected edges or faces. Here you can see what that looks like. And that is my quick volumetric lattice tutorial. Let's get back to the other upgrades. On the Z-axis, I switched out the temporary mechanical switches for inductive proximity switches. They sense the presence of these stainless steel plates on the Z-axis carriages. Their mounting location allows for the full 1245mm travel in the Z. The final upgrade is to the aesthetics of the printer. I have added 3 zones of interior lighting controlled by dimmers. The zones are the front, back, and logo, which need to be controlled separately for filming purposes. The front and back zones consist of standard V-shaped channels with extra bright dual row LEDs. The logo backlight was created from these LED sheets. This is my new favorite lighting product as the sheets are flexible and can be cut into a variety of different shapes. So much easier to install for lighting flat areas, which would previously require snaking LED strips back and forth. To mount the sheets, I printed a back panel on the Giga out of IC3D's recycled PET G. This color is honey. As an aside, this is the perfect application of the Giga, a part with a large cross-sectional area but short height. Also, I'm not in a rush to get this printed, so the Giga could take its sweet time with it. And it did, at almost a 2-day print time. I'm also printing cable channels out of IC3D's black PET G to tuck away the wires that run along the top perimeter. These will take a little while, so I may or may not have those finished before the video goes live. While there are still some smaller details that need to be buttoned up, the last real challenge is managing the extruder's cables and the pellet tube. You can see that I anchored the wires down with this printed part on the carriage and then wrapped them with this nylon Velcro sleeving. To pull back any slack in the line, I'm using a retractable cable line as I've done previously, but this will be a problem when the extruder is at max height due to my low 8-foot ceilings. I'm thinking about designing a motorized cable retractor that feeds the pellet tube and wires from behind the printer, similar to those found on large robotic arms. Definitely let me know in the comments if you have any suggestions. It's time to start printing with the extruder. I've been waiting for this moment for over 6 months. Of course, I had to rework almost the entire printer, from the motion system to the electrical wiring, to support this behemoth of an extruder. So hit that like button if you're excited to see it in action. We're going to start off with a vase mode print to test the max extrusion rate of the tin. The feedstock will be recycled PET G pellets, which will be extruded through a 5mm diameter nozzle at a 2mm layer height. This large extrusion width means that the output of the extruder will limit our throughput and not the travel speed of the printer. The print will start at 22mm per second, which equates to 1 kilogram per hour, Every 5 layers or so, the volumetric flow rate will be increased by 1 kilogram per hour with a proportional increase in speed. As we climb to these higher speeds, it's evident that the previous layers don't have time to fully cool because the momentum of the extruder is pulling previous layers towards the center, which is why the edge is sloped. Even though I have 3 blower fans running at max speed on the print head, this is not enough cooling. In the future, printing larger objects with longer layer times would help with this problem, but it should not be understated how important cooling is for high extrusion rates. At 5 kilograms per hour, we start to have some irregular extrusion. Now I'm sure that if I optimize the barrel temperatures or switch to a more forgiving material like PLA, that I could unlock the advertised 5 kilogram per hour. But for this demo, I'm limited by layer cooling time, so I will move on to some other prints. Most of my past large format prints have been in vase mode, where the object is printed in one continuous and smooth extrusion. As mentioned in my last video, my old lead screw setup was slow, so any non-printing moves, such as moving to a separate feature or part, would drastically increase the print time. Also, the extruder has a large holdup of molten plastic, leading to oozing and drool whenever it traveled. And yes, I tried all the different ways to manage this drooling, from pressure advance to coasting, but when the travels are so slow, more plastic can melt and follow its way down the screw's flights. But with my new rack and pinion actuators, I can now achieve 3 times faster travels. So let's tackle a normal 3D print, and what is more stereotypical than good old Benchy? I've scaled this model to 7 times its original size. I've switched to a smaller 1.5 millimeter nozzle and set the layer height to 1 millimeter. I added some white colorant in with the recycled PETG pellets. Each feature of the print has a different speed, but after the first layer, the sparse infill is maxed out at 180 millimeters per second. Any outward facing feature is at 50 millimeters per second, and internal perimeters and solid layers are at 70 millimeters per second. The travel between printing moves is also set to the max 180 millimeters per second. I should make it clear that even with my printer's faster travels enabling significantly less oozing, this model is still not ideal for a pellet extruder. You may notice some gaps and inconsistencies in the extrusion. The reason for this is complex, but screw extruders function by building pressure in the barrel to force the molten material out of the die or nozzle. This pressure can take time to build, so constantly stopping and starting the screw's rotation for ending and beginning new print segments can lead to these observed artifacts. The Archimedean cord infill does not suffer from this problem because it's largely printed with one continuous arc motion, which is why I selected that infill type. Also, you may have noticed the vibration or ringing texture seen on the outside hole. This is due to the rack and pinion actuators, which inherently produce more vibrations than other forms of linear motion. The print head being cantilevered acts like a tuning fork, amplifying these vibrations. Increasing the rigidity of the printer's frame will definitely help and is a future project. Anyways, enough with me being critical about the print. This is an extreme test, as all future prints will be highly optimized to suit the unique characteristics of this printer, or I will be sure to print objects so large your eye won't catch the small flaws. If you were wondering, yes, this print is foreshadowing my next project, which I teased almost 2 years ago, but better late than never. With those calibration prints out of the way, it's time to print something functional. But first, a little backstory. Andy and I live in a townhouse, which is one of the reasons why this large format printer project is so crazy. But when I'm not feeding this machine pellets, I like to feed myself vegetables that we grow on our porch. For that reason, I have designed a corner planter for our tomato, cucumbers, and small herb plants. This will be printed in several parts to avoid overhangs, but I'm going to leave you with this printing montage. So with that, I'll catch you in the next one.